All right, so I'll start by a few general notes. So Flow is a seminar series on federated learning, broadly construed. So we host speakers on a wide range of topics like machine learning, distributed optimization, privacy, or even cryptography. So if you have suggestions for speakers, please feel free to send them to us, the organizers. Two quick administrative things. So if you have questions during the talk, please write them into the chat or raise your hand, and either me or Samuel or the speaker will sort of prompt you whenever a good time to interrupt is. And the second thing is that this talk is being recorded, so hopefully you're fine with that. So with that out of the way, it's really my pleasure to introduce Professor Sebastian Stich, who is an assistant professor at the CISPA Helmholtz Center for Information Security in Saarbrücken. He's now in the process of moving from his research scientist position at the TFL, and before that he did a postdoc with Yuri Nesterov in Leuven. He got his PhD at ETH Zurich in Emma Balzer's lab, I believe. And Sebastian's main research interests are in optimization for machine learning. He's also working in sort of security as well as theory of deep learning. And he's actually the author of quite a few results that the federated learning community has heard of, so including some of the first analyses of both local SGD and sparsified SGD. So today he will talk about new methods for more effective bidirectional compression for federated learning. So I'm really looking forward to his talk.
Okay, thank you, Dan, for this very nice introduction. Yeah, it's a pleasure to be here, and thank you all for organizing this series and this talk weeklies. And I mentioned before the recording started, I'm also not attending every meeting, but yeah, having the talks online is very helpful. So as Dan mentioned, we'll soon move to a new position. So reach out to me if you're interested to work with me. So I will start with the introduction, but I will kind of keep it maybe not short, but compact, because I'm assuming that most of you have attended one or two talks before mine, and all these terms like federated learning are mean something to you. So just to briefly recap, we're looking at the learning setting where we want to train a central machine learning model by accessing data that is stored on different client devices. And instead of sending this data to the central server for the training, we are interested in algorithms that can train the machine learning model locally on the device so that the data never has to leave the device. And yeah, this framework is implemented for many applications already, but I think there are more to come as algorithms improve, and also our security guarantees or other aspects will improve. So in this talk, I will take a very abstract perspective and less focused on applications, but just on algorithm design. So I will formally introduce the problem that we want to solve. And basically we can, most of the time, write our machine learning problems as minimization problems. So I want to minimize the objective function that can be decomposed or can be written as a sum of n components, where n here represents the different clients. And every client has access to a separate share of the data. So of course, maybe some data can be similar on different clients, but in general, it can be very different. And every client can either compute the full gradient of their personal objective function, or they can just access the stochastic gradients, for instance, by taking a mini batch of their local data. And as I mentioned, all these clients, they want to train a joint machine learning model. And we are now looking at to find algorithms that are efficient in the number of computations, like iterations that we have to do, And we want also to be efficient in terms of the communication. So if I have to talk to a lot of mobile phones, this will be very slow connections. So I want to either reduce the number of communication rounds, and I also want to reduce the message size sent to these clients. And I mean, in federated learning, there are many other very relevant problems and scenarios. And I think just look at the past or future talks, and you will find a lot of other topics covered. Before I go into any detail, I just somehow recap a bit on the theory so that we all understand. I mean, just to go over the notation and the basic algorithms. So the standard algorithm, that's basically all the currently used variants in practice are somehow derivations of this stochastic gradient descent. So I will mostly talk of, just mention SGD as sort of the template algorithm to explain what is going on. So in SGD, we want to minimize a loss function that is given in stochastic form, and we can access stochastic gradients. So I can either compute the gradient on a mini batch or on the full data or on a single sample. And I update my model parameters by just moving a small step into the negative gradient direction. And of course, we can come up with convergence guarantees for SGD. And in order to do that, we need some assumptions. And among the most standard assumptions is the assumption that the variance is bounded by a parameter sigma square, and that the objective function is smooth. So the gradients do not change too quickly when moving to another point. Of course, these assumptions can be relaxed or refined, or you can make different assumptions, but that's just an example of what's the most standard thing to do. And under these assumptions, we can, for instance, prove that the norm of the gradient of our algorithm will become smaller than any desired parameter epsilon. So we can prove that SGD converges to a stationary point on smooth functions. And the number of gradients that we need to evaluate or compute can be written in this form. So it's typically sigma square over epsilon square, where epsilon is the accuracy and sigma is the noise, plus some higher order terms that matter a bit less. And as soon as we make additional assumption, for instance, that the function is strongly convex or star convex, we can typically improve these rates and get a bit tighter. So we can, instead of converging to a stationary point, we can, for instance, show that we converge to global minima and so on. But we always have to think a bit, what do these guarantees mean? Because most of our theory is not really, I don't know, explaining what is going on in deep learning very well. So I think in the convex world, this theory is very strong and very precisely capturing all the main effects. But in general, for non-convex optimization, we are now a bit behind on the theory side. That's my opinion, but maybe also opinions of others. So let's now think about how can we use this knowledge or this SGD algorithm to construct a baseline for this federated learning problem. I'm now given n clients, and every client has some data. So what I could do, I could just ask every client to compute a gradient or a stochastic gradient on their local data and send it back to me. And I can aggregate all this information and update the model parameters on a server. So this algorithm works very well. We can even prove that there is a linear speedup. So this rate is for the strongly convex case, but it also holds for the non-convex cases. Then when I have n machines available that compute gradients, I can typically expect a linear speed up in the number of workers. So this sounds very good, but now let's think about how this algorithm works. So in every iteration, I have to send the model parameters to all the clients. The client computes some gradients and then send them back. So this is very communication heavy. So I need many rounds to converge. And also the number of gradients seems quite high. However, we basically know that these estimations of the number of gradients that we have to compute in total, they cannot be significantly improved. But what we can still do, we can maybe design algorithms that need much less communication or communication rounds to achieve the same goal. And this is somehow part of this talk. So we will discuss two methods that can help us to reduce the communication between server and clients. So before I start with the new things, I will finish this introduction by mentioning a very common technique that has been introduced in the past, and in particular also by Dan. He has a very important paper on this topic, and which inspired us a lot. And this is about compressing gradients. So when I go back to this picture, instead of sending always the full model parameters and the full gradient, it's very intuitive to just say, oh, why can we not compress this information and send compressed versions? And actually, I've seen Emmerich has given a talk in the past, and I think Ilias. So you're very familiar with all these methods, and maybe go to their talk if you want to know more details. So we'll keep it very brief. So what is the general idea? Well, instead of sending the full gradient, try to send a compressed version of the gradient. And by this, we can typically reduce the size of the messages that we send to some fraction delta, let's say. So, okay, I see there's something missing on the slide, but I can write this. So let's make some examples. So we can, for instance, I don't know, quantize our vectors to, let's say, 1 bit, from 32 to 1 bit. So I can achieve a compression guarantee of a factor 32. Or I can do some sparsification. I just select the highest magnitude entries, like 1% of all the entries, and I can reduce the message size by a factor 100. And there are many other schemes possible, and many are used. And I think also some low rank method is basically available by default in PyTorch at the moment. So it's very easy to use these methods. But a bit more important than the compression factor is also what is the convergence guarantee that we can prove for these methods. And somehow this is not here, but I can write it down. So let's say standard methods, they are affected by this compression ratio delta. So in standard analysis, let's maybe write here the convergence, the first term in the convergence rate for non-convex functions. Then if you just do compression without any additional tricks, we can prove that the algorithms in the worst case needs no more iterations to converge. So every message that we send is smaller, but we need more messages. So it's not so clear whether we can realize really some gains in practice. Opposed to that, so when you apply error feedback, and I will briefly mention what it is on the next slide, we can basically prove convergence guarantees of the form sigma square over epsilon square that is basically are not affected by delta. So this is okay, it's not possible that the true rate is not affected by delta, but basically delta will only appears in higher order terms. So the most important thing is that basically the main order of convergence is not affected by the compression scheme. And Emmerich has given a talk with all the details, so I'm skipping the theory for that. But just to mention how the algorithm works, the idea is very simple. Instead of applying compression directly to the gradient or to the stochastic gradient, we maintain also some sort of error buffer where we keep track of all the compression errors. And in the next iteration, I also try to correct for these past errors. So this memory or this buffer basically accumulates compression error over time. So maybe in one iteration, I can do a very large error or mistake, but if I have many rounds of communication, I can correct for that. And if you have some guarantees, or if we, for many schemes, we can prove this, if this error goes to 0, then we can recover this convergence guarantees for SGD. So this was maybe a bit dense if you have never seen it before, but I think many of you are familiar with that. So this finishes basically the intro and this recap of compression and error feedback. So are there any questions at the moment? Yeah, maybe not, or otherwise interrupt me later. So this is the old part. Now we step to some new techniques. And basically I want to mention 2 projects which are maybe still ongoing, but I think are going in nice directions, that are a bit slightly different ideas how we can reduce the communication between server and clients. Okay, so one idea is a procrastinator, where basically in one line, the idea is that we want to reduce the communication. So instead of communicating every round or after every epoch, we want to be lazy and try to detect when can the algorithm skip some communication rounds. And this is, yeah, the theory that I will present has been developed in these 2 papers mostly. And okay, what I will do now is basically guide you through the algorithm design and how can we maybe, yeah, what are the main ideas behind this scheme. So let's go back to our problem formulation. So we have a distributed optimization problem that I want to solve by communicating between server and clients. And when we study this problem, it turns out that in many theoretical proofs or for many algorithms, it's very challenging, that it's very difficult for a single client to detect when they have arrived at the optimal solution. Because let's say I'm client I, and even if I'm giving the optimal solution, like a stationary point, for which the gradient of the total objective function or the global objective function is 0, then the local gradient does not need to be 0. So if I'm just have access to the local information, I cannot detect if X star is a optimal point or not. And okay, maybe we can say it's not important for this worker to know this, but it's just an explanation of why there is a lot of complication in this problem. So for typically when the data is very diverse on these clients, that's a very challenging situation for many algorithms. In particular, this two algorithms I mentioned before, just applying compression or applying compression with error feedback, it somehow turns out that the X star is not really a stationary point. So if we would start the algorithm at an optimal solution, we would still slightly move away from this solution. So this sounds like a bit a strange property that we maybe want to avoid. So what we now try to do in the next 10 minutes, we want to design an algorithm for which stationary points are indeed fixed points. So once we are there, we will never move away. And in terms of communication, we want to achieve that once the client observes that it has converged to a stationary point, it basically stops communicating with the server. So this sounds like a good properties, but let's see if we can achieve this. So one key idea, or it's maybe not so key, but I think I use it for the presentation to explain what is going on, is that, let's say, I mean, the standard schemes, they just apply quantization directly to the gradients that they compute. But nobody forces us to use this exact compression. We could also use a different compressor. And let's say I would give you the value X star. So every worker can locally compute what is their gradient at the optimal solution or at a stationary point. And then just compress the difference to this stationary point. So this has this interesting property that once we converge to X star, this term in this bracket becomes 0. So the clients basically don't need to compress anything anymore because that's just the way how we designed this compression function. And I mean, this is still an unbiased compressor. So all the theory we had for all the algorithms before will just automatically can be applied to this kind of compression scheme. However, in practice, we do not know this value. I mean, otherwise we would have solved the problem already. So what is commonly done is to introduce just a parameter, let's call it h, and basically we want to learn this h parameter on every client. So the final algorithm or the general idea looks like this. So on the worker, I now just compress a difference between the gradients and my guessed value of the local optimal gradient. On the server, I still have to send this value to the server. On the server, I can decompress, apply the update. And of course, I mean, I mentioned before, somehow this scheme would potentially work for any choice of h, but we want to reduce the variance as much as possible. So it would be good if we can somehow design an update scheme to update this h in a way that we maybe can prove that it will converge to the desired value. So I think ideas like this has appeared in many prior works, and I'm not claiming that this is a complete list. I'm just mentioning there was this master thesis by Federated in our lab, and then there has been I don't know, more papers 2019 that use very similar ideas, but I've also seen this year on arXiv more or less the same idea rediscovered again. So it seems to seems to be useful if so many people come up with the same thing. So I've not been very specific, so I left out how this h is being updated. But this is very crucial, no? Because all these algorithms, they crucially depend how do we update the h, and this somehow this will impact the convergence rate that we can prove. But actually, if you remember the intro, I somehow mentioned if we apply error feedback, then it's not so important what kind of compression we use, because anyway, the main term of the convergence rate is not affected by the compression scheme. So let's just add error feedback on the top of this algorithm from the first slide. So I'm now additionally add this error accumulation vector. And this vector keeps track on every client on the local error that has been made in the compression. But because we do many iterations, we cannot compensate for these errors over time. And interestingly, we can prove that almost for all reasonably sensible ways to update the age, we can get the same convergence guarantees as we would get for SGD without compression. If we just look at the first term in the convergence rate, so the dominating term when the noise is high. And yeah, so I think this is somewhat interesting because it leaves a lot of freedom to now design just, let's say, scheme that works in practice, but maybe are harder to prove because we know it will only affect lower order terms. So that's, I think, yeah, that's nice, but somehow we still need to communicate a lot, even if we have error feedback. Why? Well, every iteration I've written down, we should compress something, send it to the server, and the server is doing something with it. So that's another idea that's also not new from in this paper. What could do, for instance, local steps. So instead of communicating every round, the workers, they can just skip the updates for some fixed period of time or a fixed number of iterations. So we can add here a parameter tau. I don't know, maybe we can set it to 5 or 500 or whatever value you like. And of course, it will affect the practical behavior of the algorithm. So we have to come up with, okay, good values that work in practice. But then let's think, even whatever value you choose, communication can never entirely be eliminated. After tau steps, the algorithm has to communicate. And there have been some variations of this. Some papers propose, I don't know, some schedules of this tau value. So to maybe increase it or decrease it over time. And you have to fix this schedule. And then the algorithm, just communicates whenever you allow it to communicate. But even with this idea, there is still a time step where we need to communicate. And is this really necessary? So yeah, one idea is the following. So our algorithm has, every worker has locally this error variable where we accumulate the errors that we are making. And basically we can just look at this vector and the worker can decide by itself, is the error high or low? So if the norm of this vector is large, then the worker should realize, oh, I'm in trouble, that's not good. But if the vector has norm 0, then the worker knows everything is perfect, there is a low error. So we could just use this the norm of this memory vector or this error buffer as a criterion to decide should we communicate or not. And yeah, that's somehow the main idea in the paper, that we use this norm of this error vector to trigger communications. And of course, we should compare this norm to some values. For instance, we can compare it to a stochastic gradient computed locally on the worker, or we could also use some global information if it's available. But I mean, the most important thing is that we have these triggers, and the worker can decide on its own whether it has to communicate or not. And when we do it like with this criterion or some variations, we can basically prove that the convergence rate is exactly the same as in the strongly as for SGD without any compression. So yeah, this sounds all very good. And if we now can design this update of H in such a way that H really converges to the gradient at the optimal solution, basically we come up with an algorithm that once it detects it has converged to the optimal solution, it does not need to communicate anymore. Okay, so there is even one more component, but I realize it's getting too much. So far, I've just talked about the worker side. Now, the worker can implement all this crazy scheme and decide on their own, do they have to communicate or not. And we can do this basically in the same way on the server, and then also the server can decide, should it broadcast or should it not broadcast. And yeah, this is yeah, Emmerich has had this paper on bidirectional compression with error feedback. So this is very similar to this idea. It's on the server, on the client. The only thing that has changed is that this communication is not triggered in a different way. There's been other papers that proposed lazy updates. For instance, for this lag paper, they proposed some triggers based on the Lipschitz constants on every client. So they measure how far have they moved, and they build a trigger in this way. So this is a bit different to what we propose. Let's now skip to some results, and I think that's maybe better. So what we have done here is, yeah, maybe a very small network just to demonstrate it seems to work. We distribute the MNIST data set on 10 machines so that every machine get a different data from a different label. And we just implement how do these algorithms compare. So in blue, we have standard mini batch SGD. And okay, in other colors, other algorithms. It's important to note that when I just compare the epochs, all the schemes behave roughly similar, not exactly, but roughly similar. Now I will focus on this client communication plot. Here it becomes a bit more interesting. For instance, we could now apply something like local SGD, where we communicate only after every 5th iteration or every 5th epoch. So we can now reduce the communication load by a factor of 5 almost in this for this problem. If we apply this scheme where we automatically trigger the uploads, we can reduce even much more. And if we combine it with the procrastinated server broadcasts and client downloads, I mean, then it's the performance, yeah, drops a bit. I mean, the total number of broadcasts, of course, goes down a lot, but yeah, the very best scheme is probably some mix of both or a bit in between. That's just to illustrate, okay, the algorithm somehow seems to work a bit, or in, yeah. So we had maybe a bit more realistic example, VGG 16 on CIFAR 10. And here again, we split the classes by label on the different machines. And we now observe that this local SGD algorithm where we just fix manually a gap to communicate really does not work well on this kind of problem, because the data is so different on every node. We are basically punished by doing local steps. So we are not gaining anything in communication. We are slower. So this is here the green and the blue curve overlap in this plot. But on the other hand, this because we learn this H value basically, so this drift on every client, we are now able to improve over that with these new algorithms. Okay, there's a question. I show one. Yeah, the data is distributed by label here. So we have 10 classes. So every class goes to one node. That's why this local SGD is so bad here. If we would randomly distribute the data, local SGD would also be very good, or the best actually. Yeah, let's do a kindly small ablation experiment. And this is now on a convex problem. So like rich regression, I don't know, just artificially chosen 200 nodes. And we look what happens on every node. So for instance, on node number 20, we see that it uploads at these points in time. And apparently it seems that this trigger condition really seems to work. So the frequency between upload increases, which is what we wanted. But there are other nodes or where this, I don't know, does not happen. So the upload frequency is constant. So can we theoretically understand what is happening to this upload frequency? And this is not a fully rigorous argument, but it's more a bit of a rule of thumb. So we can show under some strong conditions that the expected gap between two successive communications should roughly scale as this expression. So we observe, I think, two interesting things. So first of all, if this the difference between the nodes is large, we need to communicate less often. And this is very surprising because all the other algorithms, for them, it's a real problem if the data is different on the machines. And in this case, this somehow is to the advantage. And secondly, we see as soon as xt approaches x star, the communication frequency reduces. And actually, it could go to 0 if there is no stochastic noise. On the other hand, if the stochastic noise is positive, then, I don't know, this term will just be some constant. And basically, we're saying after some constant number of iterations, and communication will be triggered in expectation. Yeah, this is not fully rigorous. So if you have some motivation or idea to make this fully precise, I think, yeah, that would be interesting problem. So to summarize a bit, we have seen this event triggered communication as somehow the main idea. I've not showed you the exact algorithm because I think maybe there are slightly variations that could even be improved, but somehow the main idea, this triggered communication, this is the main part. So we can reduce the frequency to 0, but only if we don't have stochastic updates for the moment. So I think this can be handled by building even on top of everything some variance reduction, but I mean, this would go, I don't know, would be beyond the scope of this talk or anything, but yeah, I'm confident that this would work. And yeah, with the error feedback framework that I've not really shown, we can get rigorous proofs and also some principled way to get these triggers. I'm not saying there might be better conditions in practice, but at least this is one condition that worked for the proofs. And I don't know, in terms of experiments, there may be on convex tasks, it works excellent. On deep learning tasks, it's a bit less, I don't know, the benefit is a bit less pronounced, to phrase it like that. Because on, I don't know, in many situations, especially if the data is distributed in an IID fashion or close to the IID fashion, then all the other techniques we had before seem to work reasonably well, and this additional scheme does not give any benefit. But if there's the data is very different, I think this is very promising to go. So are there, some questions on this part, or should I skip on to the third part of the talk? Yeah, not for the moment, but maybe later. Okay, so Peter told me that I should focus only on one paper, and I was thinking, oh no, 1 hour is way too long for one paper, but I could have shown you more details if I would have devoted more time, but I was thinking, oh no, let's also include this second project. This is already with colleagues from CISPA, and yeah, it's just an idea how we could probably also reduce communication in federated learning settings. And we now maybe take a step back. So what is the problem that we want to solve? So far, I've always mentioned, oh, I want to minimize some abstract function f of x. That is, I don't know what it is. And we just design blindly some optimization algorithms that can work for all arbitrary functions f. But actually in deep learning or for most federated machine learning applications, we train some neural networks. So we could maybe take the structure of these neural networks into account to design better compression schemes. So in particular, we know the number of parameters of a typical neural network is huge. So even if we reduce the communication to 10% of the parameters or to 1% of the parameters, it's still a huge number. No, so we can now either work very hard to improve the compression scheme, or maybe it's simpler to reduce the number of parameters of the network. So let's try with this idea. So I just delete half of my network, or I don't know, 3/4, and get now a much smaller network. And typically this can be done. Now we have these layer structures in neural networks. I could just crop my network after a few layers and now train a smaller model. And I think for many data sets or for many tasks, this gives already very good accuracy. And if you're happy with very good accuracy, I mean, why don't we do this? But now you can say, oh no, I'm not happy with good accuracy. I want the best one. So one idea that we could do, we could now try to grow these networks as we train. So we can first train the small model. This is very communication efficient because we have only a few parameters that we have to send between these clients and the server. And if you want to increase the accuracy, we can start growing the model. And okay, to make this a bit formal, but I think the picture was much nicer. I can write my neural network as a composition of different layers that act, I don't know, one after the other on the input. So this could be blocks or simple layers. And there is often like a head at the end, like a fully connected layer where we learn some classifier on the learned features. So if I denote my parameters as like x1 is the parameters for the first layer, x2 the parameters for the second layer, I could now just start by training the parameters of the first layer with a fully connected layer on top of it. So this head layer we need to add to train the first part of the network. Now, when I want to grow my network, I can now skip to the next stage. I throw away this old head. I initialize the new additional parameters that I added to the network, and I now train the new model. And okay, there is a small technical detail. It turned out to be very helpful to use some warm up for these new parameters. So instead of randomly initializing, it's good to freeze the old weights and slightly train these new weights for a few iterations. Yeah, that's okay. A good question. I will come to that. So this is somehow very much borrowed from the, I don't know, work in computer vision, where they propose to design a generator that generates images, and they basically design it in a way that it can first generate low resolution images and then increase the resolution over time. So this is not a new idea, but I think that's as far as we know, the first time that we tried to use this to train neural networks in a federated fashion and try to achieve communication reduction. So this is a bit more practical project. So a few practical comments. So what we do so far, we always grow the models to full capacity. And basically we spend roughly half of the training on the full model and distribute the rest of the budget evenly across the growing phase. But if you want more aggressive compression, you should maybe consider stopping after the first, after training the first model, because then you have achieved the highest compression ratio. There is this warm up and also some learning rate restarts that we use. So some results, just like a demo on a centralized setup. So this plot shows 4 different models trained on a CIFAR 100 dataset. And we basically, this is on a single worker. So we basically demonstrate here what is the expected reduction we can hope for. And it seems to work best like on this red curve, VGG 19. And also when you look at the learning curve, the accuracy drops, increases very rapidly. So this is even on the smallest model, we can get very, very good accuracy. And this is the speed up. So to achieve 100% performance or slightly more than what end-to-end training achieves, we can achieve this by roughly reduced cost of factor 5. If you're happy with losing 2% of your final accuracy, you can sort of increase the compression ratio even more. But of course, there is a trade-off that you have to decide depending on the application. We now implement this on several federated learning setups, and all these setups are somewhat borrowed from some papers, so they can be compared to the respective paper. And for instance, we take the eMNIST dataset that has 3,400 clients or users that have written these numbers, and in every training round, we activate 64 of these clients. So these are just the numbers that we take from the original paper. And yeah, we measure a bit across different tasks and models. And we can show that even if we don't do anything on top, just as progressive training, we can reduce the costs up to some factors, but it's not, it always comes with a slight loss in performance compared to the baseline. And I think, yeah, the most impressive numbers are achieved by just combining everything. So we do progressive training with compression on top. And yeah, these are all exactly on the same model and data set, but with different compression schemes. And okay, the most impressive one is maybe this data point. That gives a 50% cost reduction and only less than 1% loss in final accuracy compared to training with always the full model and the full gradients. Okay, so there was a question in the chat. Does this come with theory? And yeah, there is a, yeah, that's a bit what I'm not so happy with. We can prove that this scheme converges to a stationary point. But we cannot prove that we are better or faster than standard training. And I think this is a very limitation of, let's say, the theoretical framework that we have in general. So we cannot, I mean, we mostly prove convergence to stationary points, but we cannot argue this stationary point generalizes better than the other one. So, and here we would really have needed such a theory saying, even if training the small model, we generalize well enough, but yeah, somehow we cannot guarantee this. So I think on the plus side, this is very good when we can stop the training before growing the model to the final size. But we somehow lose the benefit of compression. I mean, the compression ratio is 0 or when we have to grow the model to the full size. And I think this is very general, interesting direction. And also there's several orthogonal works on this. Like the goal in model compression is also to come up with models that are compressed, that can be sent to the clients at a reduced cost. There's also model distillation for federated learning, where we aim to have slightly different models on every client and also much smaller models. And then we can, yeah, then the problem is how can we aggregate the knowledge of all these different models? But this is going a bit in the same direction. We can reduce the communication when we basically change the training objective on the devices. So I think I'm running a bit out of time. So just to conclude, we have seen somehow two main directions, not too many theoretical results. So please check also the papers. The first one was about this time varying compression or communication schedules. And I think the important part is that it's adaptive. So we can, the scheme can detect when it has converged and stops communicating. So the second direction was about maybe we can even achieve higher compression ratios by changing somehow the objective function that we are using. But of course, this might depend a lot on your desired application or problem. And yeah, I think this is could maybe be interesting to discuss a bit more about what are your opinions on this, and maybe we can even prove that this works. So thank you for listening, and yeah, are there more questions? Thanks.
All right, thank you very much for the talk. I guess I'll get things started with maybe two very quick questions from my side. One, so I found kind of the results from like for the kind of first result for the first algorithm that you gave, quite promising in a way, because I mean it's kind of a fairly difficult setting if you're actually just partitioning by class.
Mhm.
So one question I had was, did you try this on even harder settings in the deep learning kind of environment where, let's say you have more, like on CIFAR 100, you'd have even more classes.
Yeah.
So then it would be even more fine-grained, perhaps more difficult. I mean, you could also go to ImageNet where
Yeah.
it would be even, right. So
yeah, even more. Okay, so
yeah,
this is a one step in this direction, but it's a okay. Yeah, I think that the problem is, yeah, we did not go to 100 clients.
Yeah. I mean, that was going to be my question.
Yeah.
I did.
So I agree with you that it would be more getting, if we can come up with some more impressive.
No, I mean, well, I found these early results quite impressive, to be honest, because data heterogeneity is pretty significant in your case. But I was just wondering, like, if at some point the algorithm could kind of break down, or you, maybe on the other hand, it would just learn to sync at every step or something like that. That would be quite interesting. Okay.
Yeah. Maybe one other comment. I think we observed basically the noise. I mean, in this, if the noise is too strong, one should be very careful on how to update all the parameters and things. And I think there we have not really, we have some rule of thumbs that maybe work, but it's not like we have very rigorous guarantees that always work. And so, I mean, on the convex problems where we have good understanding of how things should work, it really works. But on many deep learning tasks, I think the noise is a bit too strong, and we need to investigate a bit further.
Is there some not trivial amount of tuning that you have to do, which is kind of data set specific or something like that?
Yeah, exactly. Yeah, I mean, there's kind of a few hyperparameters. No, the update of the age, there we use just some momentum estimate, and also this trigger condition. I mean, we can be a bit more relaxed or a bit more strict, and for all these experiments we use the same setting to make it comparable. But we observed when trying on ImageNet that these settings did not work so great. So yeah, that's a bit ongoing research.
So I think Samuel, maybe you can unmute Eleanor so he can ask this question. Otherwise, I can read it.
So the question is very easy. What framework do you use to run the experiments? Was it PyTorch or JAX or FedJAX? Thanks.
No, it was on PyTorch. And okay, I will check on what is the status on on releasing code, or yes, I think that would be helpful. But yeah, I don't. Okay. Yeah, I think there's no public code available yet, but okay, I will can send you a message once we have it or so. That's good. But good that you're interested. Thanks.
I also had a comment regarding, I think you stopped at some point and you kind of pointed to this result of Frederick, where he does essentially this kind of coding of the distance, like coding of the update, right? I usually call it different coding, and I think I've seen it. I mean, there are way more instances of this, and I think at least we have used it in 2 different papers only this year. So it's like usually the problem is that you have a quantity which you want to quantize, but its norm is large. So then the quantization would actually just blow up, like the error would just blow up. And then you just do this kind of difference coding, like you estimate the differences between inputs, and then you code. And also, I think that this is actually, it's quite unfortunate that Frederick never actually published his master's thesis because this is actually a pretty nice trick.
Yes. No, I think that there are many. Yeah, I think that's, yeah, exactly. There are countless examples, and yeah, I think this is really, it seems to work reasonably very well. But yeah, interesting.
All right, so I don't see any other questions from the audience. So I think, oh, sorry, there's actually one. So I think there's one on the second part. I'll let Konstantin ask it.
Thank you. Thank you for the talk. So the question actually, people in deep learning tried different heuristics to partially update parameters or optimization variables during training. Did you spend time to look into these heuristics, and what is, in your opinion, is more promising from theoretical point of view?
Yeah, okay, that's different. Okay, let me go to this picture. Okay, let's say in the course of this project, we did not experiment much with this idea. No, I mean, we compared to some baselines, like basically freezing the parameters of the last layer and just training the first, or vice versa. And yeah, this did not work so great. So this cropping the layers entirely was somehow the best. But in a other parallel project, we basically, there was a paper on slimmable neural network training. I don't know, maybe 2 years ago or 3 years. I forgot. I can look up the reference. And they proposed basically somehow to train limited width networks. So they would freeze part of the weights and only update the weights in this layer. I mean, in this smaller width network, but then from time to time, also the parameters of the full model. And I think this is this also allows to reduce the size of the model. And basically you can adaptively turn on, do you want to use the small or the big one? And yeah, this is a bit, maybe using a bit more this parameter freezing, unfreezing. And yeah, we also observed this works quite well. You're not limited to taking just small width networks. You can use arbitrary patterns. And yeah, this looks also a promising direction to me. Yeah, okay, no,
Thank you.
Yeah, thanks. Okay, Ilias also had this theory result. No, but this is, or this question on the theory, but this is basically what I'm saying. No, we cannot prove. I think this is a more general problem. So we cannot.
Yes, hi Sebastian.
Hello.
Yeah. Yeah, you just said like we cannot improve that improvement, right? But my question is that maybe the problem is like even like that we cannot show it's
not worse. Yes, yeah. No. I mean the thing is that the training trajectory is really changed. No, we are not saying, oh, we will exactly recover what the standard training is doing. So we will end up converging to 2 different stationary points, and hopefully both are maybe global solutions in the over-parameterized case. But I think this is missing, so we cannot prove this. But I think also for more general settings, now we cannot prove that Adam converges to better minima than SGD or so. So I think that the question is more deep than just
I see.
For this scheme or so. So it's
yeah, I see. And it doesn't make sense to look into this in convex case because it's not a full, yeah.
Yes.
Yeah. Okay, thanks.
Yeah.
All right. So I think with that, we'll thank Sebastian one last time for a very nice talk. And yeah, see you next time.
Yep.
Bye-bye.
Okay, thank you and bye.